Hello and welcome back. I'm Adam with Push the Envelope, the channel that gives you everything artificial intelligence and machine learning. Today is part 3 of our Titanic data set and using machine learning to solve it for beginners. And with part 3, now that we have all of our data pre-processed and ready to go, we are going to feed it through our very first machine learning model in this series. And that will be the random forest algorithm. If you haven't heard of random forest or haven't used it before, go ahead and check out the video before this, and I'll have a link right now. And just go over a beginner's guide to what random forest actually is. Definitely useful if you haven't used it before or haven't heard of it, and definitely recommend checking it out before this video. Also, if you haven't seen the first 2 parts of this series, you definitely need to check those out because I'm going to be starting where I left off in those, where we did a lot of pre-processing to the data, filling in missing values, binning a whole bunch of values. So if you haven't seen those, go check those out right now and then come back. For everyone else, let's go ahead to the Jupyter Notebook and get started with putting our random forest model into action. Okay, as you can see, we are right where we left off in the last video. Again, if you haven't seen those first 2 videos, go check them out because you have a lot of pre-processing stuff that we need to do. But we went through, filled in all the missing data, binned all of our different categories, and now we're ready to start passing it through our model. So we're going to import some things, import our models and some more pre-processing techniques. And to do that, we're going to use scikit-learn. So from sklearn dot ensemble, we are going to import the Random Forest Classifier. That's what we're going to be using to predict our data. Next, from sklearn dot model selection, we are going to be importing train test split randomized search CV and grid search CV. This is going to help us split our data into training and test sets, and along with help us fine tune our hyperparameters. Next, from sklearn dot metrics, we are going to import accuracy score. This is going to help us predict the accuracy of our model predictions. And the last thing is from sklearn dot pre-processing, we are going to be importing min max scalar. Okay, if you aren't familiar with any of these, I do have a scikit-learn tutorial that you can go ahead and check out, and I cover pretty much all of these. But go ahead and import those, and we can start. Now, there are a couple things that we need to do to the data before we actually can feed it to the model. So first, if you remember up at our data, we were talking about the passenger ID before and how we weren't going to use that for our model. So instead of removing it, I'm actually just going to make that the new index. So combined underscore PD dot set underscore index. I'm going to set the index to passenger ID. And I need to pass it in place is equal to true because I'm not reassigning the combined PD. If I go ahead and print that out, you can see it just moved that passenger ID to be the new index. So now when we feed this data through the model, it will ignore the index and ignore the passenger ID. Okay. One more thing that we need to import that I forgot about. So from sklearn, again, dot pre-processing, we are going to import label, that's a capital L, label encoder. And I'll go over what label encoder is in a second. So if we go back up to our data, we have a lot of strings or like these intervals right here, and those are great for us to analyze, but the model is looking for things that are in number form. So we need to convert all of these different strings to be integers that are unique to whatever the strings are. So for instance, the sex, we have male and female. So we want 2 unique integers, probably 0 and 1, in order to give the model something that is in the form it is looking for. So we are going to create a new data frame called label encoder. That's just going to be equal to combined PD dot copy. So I'm just copying what we have in the data frame into a new variable, just so if we happen to mess up, we don't have to run the entire script over again. We can just come back up here and import it from scratch. Okay, now we are going to make something. Actually, the first thing we need to do, some of these are in string form, some of these are in integer form, and some of these are in interval form. So we need to get them all into some common form, and it's either looking for integers or strings. So I'm just going to go ahead and convert everything into a string just to make it easier for this. So I'm going to take label encoder. I'm going to say that's equal to label encoded dot as type. Sorry, this is no underscore here. As type string. So again, converting everything in the data frame to a string, because that is what the label encoder is going to be looking for. That or integers, but I can't convert most of these integers. That's the problem. So we're going to take label encoder, and we're going to say label encoder dot apply. Let me scroll down a little bit. And we're going to apply the label encoder function. So the one we imported, label encoder, capital this time though. And we are going to do a dot fit underscore transform. And so this is going to take everything, and the label encoder function is going to assign it a unique identifier, a unique integer based on whatever the string value is. Let me go ahead and display this. All right, and you can see where we had strings before, they are now unique integers based on whatever that string was. So we're getting closer to what the model needs. There's one more thing that we need to do. Now, as you can see, for something like the age, there are values from, I can't remember how many bins we had. Maybe we had 7 bins. So there are going to be values from 0 to 6 for each of the unique values. Now, the problem with label encoding and the problem with feeding this through the model is that for any category that is labeled 0 to 6, there's an inherent bias that value 1 is greater than value 0, and value 5 is greater than value 4. And there's a hierarchical order based on whatever that is. Now, for a lot of these, like the age or the fare, we do want that because a greater age says something and a greater amount that you paid for your ticket says something. But for things like sex, 1 is not necessarily greater than 0. It's just that is the label. So we need to do something called one-hot encoding in order to get rid of that bias, and so the model doesn't think that whatever the 1 value is greater than the 0. And there's, besides the sex column, we need to identify some other ones too. So like the embarked location, there's just 3 locations, and not necessarily one is greater than the other. And another one is the title category. Now, there are some titles in there like nobility where we could assign some hierarchy, but when we start looking at like the Mr. or Miss title, it's hard to come up with some overarching hierarchy where one is greater than the other. So we're just going to do one-hot encoding for that as well. To do that, we're going to, again, define another data frame, and that's just going to be the copy of the label encoded data frame. Just in case we do something wrong and need to backtrack, we are going to take the one-hot encoded data frame, and we're going to say pd.getDummies, and you're going to see what this does in a second. We're going to pass it that data frame, and then we're going to pass it the columns that we want to be one-hot encoded. So this is going to be the sex column, the embarked column, and the title column. And let me go ahead and display one hot. You can see what this actually does. So before in the sex column, we had zeros and ones, depending on what the sex was. One hot encoding, and they pushed all these to the right. But one hot encoding takes that column and it makes it into however many unique variables you have. So for instance, sex had zeros and ones. Instead of saying that 0 was assigned to, if I come up here, 0 was assigned to male and 1 was assigned to female, I'm just going to make two columns, one for male and one for female. And if it is a male, then I'm going to put a 1 in the male column. And if it's a female, I'm going to put a 1 in the female column. That way, I don't have any hierarchy. It's just a 1 or a 0, depending on if it's in there or not. And so you can see 2 columns for the sex column, 3 for the different embarked locations, and 7 for the different titles that are in there. And this is what we want. We want the hierarchy kept for the ones that it should be and removed for the other ones. So at this point, we are now ready to start passing it into our model. We've done all the pre-processing we need to, except for one thing, but it's very easy, and that is we just want a min-max scale so that everything is between 0 and 1. And typically that's what algorithms will want, is values between 0 and 1. And so we will do that right now. But first, if you remember back at the very beginning, we had two data frames that we were working with, the training data frame and the testing data frame. And the difference was the training data frame had the known survival rates already attached to it. So in order to train and test our model, we need only the ones that we knew the end survival rates for. So we need to go ahead and, from this combined data frame, extract all of the training indices, only the training indices, because those are the ones we have the known values for. To do that, find a new variable called x. We can take the data frame that we just made, one hot, and we can do a dot locate using the training IDX variable that we created at the very beginning. Those are all the indices of the training passengers. And doing that, we can also do dot values. This is just going to get rid of all of the index columns and the column headers. Another variable that we made was the survived variable at the very beginning. We're going to pass that in as y, and we're just going to do survived dot values. So now we have our x and y values that we're going to be using to train the model. Like I mentioned, we need to do min-max scaling. So we're going to define a scalar that is equal to min-max scalar. This is the one we imported from sklearn. We're going to fit that scalar. So scalar.fit with our x data. And then we're going to make a new variable called x scaled. That is going to be equal to scalar dot fit underscore transform, and we're going to pass in x. So all we're doing is creating a new variable called x scaled that is going to scale all of these values from 0 to 1. And now we can go ahead and create our training and testing splits. So x train, x test, y train, and y test is going to be equal to train test split. We're going to be passing in the x scaled values and the y values. We're also going to say I want my test size to be equal to 20% of the data. And in order to make this repeatable, I'm going to pass in random state equal to 0 so that I get the same train splits every single time. If you don't want to copy exactly what I'm doing here and you want to get slightly different results, get rid of that random state or change the random state to something else. Last thing I'm going to do, I'm just going to print xtrain.shape, xtest.shape, ytrain.shape, and ytest.shape, just to make sure we have the data in the proper forms, and we do. So we have 712 training points and 179 testing points. All right. Now that our data is ready to go, we can train our classifier. So classifier is going to be equal to the Random Forest Classifier. I'm going to force the random state again to be 0, just so you can make this repeatable. I spelled random wrong back here, so just make sure that's spelled right. And now that we have our classifier, we can fit our training data. So clf.fit xtrain ytrain, and we're going to go ahead and do a dot score to score it against the test data, so the x test and the y test. Go ahead and run that, and as you can see, we are getting an accuracy of 0.79. So 79%, that's not terrible. I think we can get better. So let's see what we can do to do that. And in order to boost this performance, we're going to need to start looking at some hyperparameters. So we're going to define a params variable, and it's actually going to be a dictionary of different hyperparameters that we're looking at. So the first hyperparameter will be the criterion. And there's going to be two values that we can use for criterion. We can use Gini, or we can use entropy. Okay, so we're going to take both of those and we're going to look at each one of those. Other hyperparameters are going to be n estimators. So this is the number of trees within the forest, if you remember what random forest is. And we're just going to create a massive list of different estimators. So let's go 20, 50, 100, 200, 300, 400, 500, 800, and 1000. Now, be warned, the number of estimators, the more that you create, the longer it's going to take to train your model. So the more that you create and the bigger the number are for the estimators. So these are what I'm going to go with for now, and we're going to use randomized search to figure out which ones are best. Next, we're going to do max depth. That's how deep your trees will be. And I'm just going to do a whole bunch of values. So I'm going to do np.arrange, and I'm going to do 3 to 50. So that'll give us a whole bunch of different depth values. I will do min sample split. So the minimum number of samples is split for the tree. And again, we're going to do a whole bunch of different values. So I'll do np dot arrange. Let's do a bunch. So 1 to 1,000 maybe. Let's do 1 to 1,000. Okay, so min samples. Now let's look at max features. So this is the max features per each tree. And you can do the square root of the number of features, or you can do the log of the number of features. And the last one we will look at is the max samples. And we'll do a bunch. So these need to be between 0 and 1. So I'll do linspace. So np.linspace, I'll do it from 0.1 to 0.9 with 10 values. So this should go up every 0.1. And we'll stop there. Those will be all the parameters that we'll look at. We are going to define a new model called Rand Search. And Rand Search is going to use the Randomized Search CV function that we imported from sklearn. And it's going to randomly go through all of these parameters to figure out which is the optimal setting in order for the model to be trained. Now, it's not going to test every single one of them. It's going to randomly sample this space that we just created. And that is what randomized search is versus grid search. Now, randomized search is going to look for an estimator. So in this case, we're going to use the Random Forest Classifier. I do need to pass in my random state again just to make sure it's repeatable. I'm going to do random state equals 0. Okay, now I'm going to pass in the parameters that we just created. So this dictionary that we just created. I'm going to say I want this to be scored based on accuracy. And I do need to pass in random state to this as well, because this is randomly going to sample the space, so I want it to be repeatable. And then I'm going to do cross validation. I'm going to set that equal to 5. Okay, now our model is defined. We can go ahead and do a rand search dot fit. And again, we're going to be fitting it to the X train data and the Y train data. Now, what is this going to give us? Well, it is going to give us the parameters that it found to be optimal when it did a random search, and it's going to find whatever the best score that it came out to be. And so we want to print both of those. So I'm just going to make a new variable called random params, and that is going to be equal to rand search, so our model that we just made, dot best underscore params underscore. This is going to take the best parameters that it found, the optimal parameters that it found, and save it as a variable. And we can go ahead and print those. And I'm just going to do a divider so that we can separate all of these. Now, that will give us the parameters. Now I want to see some of the accuracies. So if I print the training accuracy, that's going to be equal to the rand search dot best score. So just like best params, this is best score. And that's going to be the best score that I was able to find with the optimal parameters. Next, I want to do the test accuracy. So I'm going to go ahead and actually just predict our test data using the model that we just trained. So predictions will be equal to rand search dot predict x test. Passing in the x test data to give us what the model is predicting it, and now we're going to go ahead and just compare that to the real results since we have those. So I'm going to print test accuracy, and that is going to be equal to accuracy score. This is the function we imported from sklearn. We're going to pass it in the predicted values and the real values. In this case, that would be y test for the real values. Okay, we have gotten all of that. Let me go ahead and run this, see if I have any errors. Seems to be working, so I don't. Now, depending on what values used for your parameters, this may take a while. Now, random search is not going to go through each and every one of them, so random search will go faster than, let's say, grid search, which does every single one. But just be warned that this could take a second to load. Once this comes up with our parameters, we're going to take what the random search algorithm learned to be the best parameters, and we're going to feed that into a grid search. Now, like I mentioned before, a grid search tests every single combination of parameters you have in your dictionary instead of just randomly sampling it. So as you can see, we printed out what it found to be the optimal parameters, and it printed out our score. So we did improve. So we had 79 accuracy before. We're up to, on the test data, we're up to 83% accuracy and 82% accuracy on the training data that was held out. So we definitely have improved a lot. And now let's see if we can continue to improve upon that by taking what we learned here. So I'm going to define, I'm basically going to take everything I did here. So let me go ahead and copy all of this stuff right here and put it down in the next cell. And I'm going to start changing some of the names. So instead of a rand search for the name of the model, I'm going to do a grid search, and that is going to be using the grid search CV. Now, grid search CV is going to take the Random Forest Classifier, it's going to take the parameters, and it's going to score it based on accuracy. Now, grid search doesn't have any randomness associated with it because it's testing everything, so I don't need the random state anymore. I'm going to change rand search down here to grid search. And anywhere it says rand, I'm basically just switching it to grid. So bear with me as I change everything. And one more. Okay, now that we have that, I don't want to go through all of these parameters that we did before. Instead, I want to learn from the randomized search. So that is going to be done by taking some of these values, like the number of estimators, And we're going to create a new variable called number estimators. That is going to be equal to np.linspace. So we're going to take a whole bunch of values between two, and we're going to pass in the random params. So all of these parameters that we came up with, I want to know what it came up with as the best estimator. And I want to, let's say, subtract 10 from that number. And I want to go from 10 below it to 10 above it. So plus 10 on this side. And I want maybe just 3. So I want 10 below, the middle, and 10 above. Again, if you do a lot of these, especially for grid search, it's going to brute force every single one of them. So it's going to take you a while to do. Even with the parameters I'm going to do here, it's going to take a while. So just be careful of, not careful, but just be aware of how long it may take you for the amount of parameters that you're trying to search for. Okay, so this is going to give us 10 below, the middle, and 10 above. Now, this is automatically going to make it into floating points, so I need to cast this using dot as type back into an integer, and that takes care of the estimators. Now we're basically just going to continue to do this for any number value. So min samples split, that's going to be equal to np.arrange rand params at min samples split. So we're passing in what it found right here, the 16 value, into here. I'm going to test 3 below it, and we're going to test all the way up to 3 above it, every single thing in between as well. Okay, so 3 below, 3 above, same thing as before. I need to go and cast this back into integer form. Okay, takes care of 2 of them. Next one would be the max samples. I'm going to go back to using linspace. And the reason for this is because this is going to be a value between 0 and 1. So I'm going to take the random params at max samples. And this, again, value 0 to 1. In this case, the max samples was 0.63. So I am going to say, I'm going to subtract 0.05, and I'm going to add 0.05 as my bounds. And I am going to take 6 samples, maybe. So this is going to give me 6 values between these two. I don't need to cast this one because I want it to be floating point, not an integer. So don't cast this one. And then we'll work on the last one, which is max depth. And max depth is going to be equal to np.arrange rand params at max depth. And we are going to go ahead and subtract. Let's do 2, I guess. Yeah, let's do 2. No, let's do 5. We're gonna subtract 5 and we're gonna add 5. So those are our 2 bounds. Let me copy this over. Okay, and then we do need to cast this one as type int. And there we go. Those should take care of all of our number values, and we can start passing things into here. Now, for the criterion, we're just going to straight up pass whatever this came up with. So in this case, Ginny. And so we are going to, within the criterion parameter here, we're going to say this is going to be equal to the rand params at criterion. And that will take care of that one. Number of estimators, we're going to pass in the values that we just created, and we called that number estimators. Max depth, same thing. Min sample split, same thing. Max features, we're going to import what the one before said. So rand params max underscore features. And as you can see from up top, max features was equal to the square root of the number of features. And lastly, max samples is going to be equal to the max samples variable that we just created. Okay, now we should be ready to run this, assuming I don't have any errors, which it doesn't look like I do. Now, disclaimer, this will take a long time. We have a lot of parameters and fairly big number of estimators that we are trying to sample through. And so this will take a while to run. Now, also, you should be careful. I didn't put it in here because I knew what these values were originally. But if you have really small values and you start subtracting 5 or adding 5 to them, you may hit the bounds of what the parameter wants. So for instance, the max depth can't be below 1. So you need to, in here, cast so that any value below 1 is just removed. But again, this is going to take a long time. So I'm going to pause the video here, and I'm going to come back once my model is trained, so you don't have to sit here and wait for it to load. So be right back. Okay, so as you can see, our model finished training, and we ended up achieving a better accuracy than the randomized search. For the training accuracy, we were slightly lower for the test accuracy. But overall, it did work, and it spit out what it found to be the optimal parameters that we can go with moving forward. Now I'm going to stop here for the random forest. Things we can do to, in the future, increase the accuracy of the model would be maybe we need to go back to our features and we need to create bins that maybe are smaller, or we just restructure the bins a little bit for some of our features in order to make it a little more precise. Also, we could do some feature engineering, maybe come up with some new features that we could use to make this prediction. Whole bunch of different things that we could do to the data. We could also try different models, which what we'll be doing in the next part. We will be using the AdaBoost model, so stay tuned for that. But for now, this is as far as we'll go. Thanks for joining, and I'll see you in the next video.